Okay, this is that first class that occur in a lot of science classes where we just kind of talk about the basics before we really dive into what we're actually doing. So with that, we'll just kind of go into some basic definitions. So for example, what is statics? Well, statics is a subcategory of engineering mechanics where engineering mechanics looks at how things are, how they behave when they're subjected to forces. And statics specifically looks at when things are stationary or in equilibrium. Okay, so everything we're going to look at in this course is basically not moving. Okay, so a few definitions that you all know, but we have to put a definition to just so we can have a starting point. First is length. So we all know what the length of something is. It basically locates the position. Time is a succession of events. Okay, we'll get into units in a little bit and talk about that. That might be a little bit more beneficial. Mass, uh, in chemistry, they talk about this as the amount of matter in an object. When we talk about engineering mechanics, what we're really talking about is a body's resistance to the change in velocity, and this really is based on Newton's laws of motion, which we'll get to in just a second. And then the final thing is a force, and this is just basically some sort of external push or pull on an object. Not the best definition, but as we get through and going, this will make more sense as we talk about things. So everything we're going to talk about in engineering mechanics, we'll be talking about what we call Newtonian mechanics, which is basically Newton's laws of motion. There's four basic laws that we're going to look at. The first is the first law, and that is basically an object in motion tends to stay in motion unless acted on by an outside force. Object at rest tends to stay at rest. We call this the inertia law or the equilibrium law. You've probably heard this before. Now, the second law is the equation that many of you may know, some of you may not, and it's basically defined as the force on an object is equal to the mass times the acceleration of the object. This is basically what gives us our definition of mass, which is that force and acceleration are related to one another, right? If I put a force on something, it'll accelerate based on how much mass it is. Okay, so the more mass I have, the more force is going to need to get the same acceleration, that sort of thing. Now, this is not actually how Newton talked about it. He talked about it with respect to momentum, but this is how uh, elementary Newtonian mechanics, this is what we think of as Newton's second law. That is force on an object is equal to the mass of the object times its acceleration. Now, the third law is another law that you all heard of before. Every action has an equal and opposite reaction. So every force has a counteracting force to it. So if you hit a table or something, the table hits you back with the same amount of force, just in the opposite direction. So forces are always paired up with one another, right? So every action has an equal and opposite reaction. The last law of Newton that we're going to use, and we won't really use the actual law of gravitation, but we use gravity a lot because we're on Earth. Gravity is always acting on us on Earth. And you can see that that law is given right here. Universal gravitation constant times two masses times the distance, or divided by the distance between them squared, right? So any two masses have um, a gravitation between them, okay? The thing is on Earth, there's this one mass that kind of dominates everything, and that is the mass of the Earth. So if I have an object, even though I might have two objects close to one another, uh, yes, there's a gravitational force between them. However, neither of them are as big as that gravitational force with the Earth itself. Okay, so what we basically do is when we think about gravity, again, all of our problems will be taking place on Earth. Okay, so universal gravitation constant is just that, is constant. We're going to assume the mass of the Earth is constant, even though satellites are leaving and meteorites are hitting us, and different. But in general, we take the mass of the Earth to be constant. And then r, which would be the distance between the center of the objects, is basically the radius of the Earth, right? The distance from the center of your object to the center of the Earth is effectively the radius of the Earth, which we will also assume to be constant. It does change a little bit if you're in Death Valley or on Mount Everest, right? That sort of thing, but pretty small differences when we look at it. So if we lump those together, then we have what we call the acceleration due to gravity. Again, that's the universal gas constant times, not gas, gravitation constant times the mass of the Earth divided by the radius of the Earth squared. That's the acceleration due to gravity. Okay, so the weight or the force that gravity places on an object is just the mass of that object times the acceleration due to gravity on Earth. And we're going to get into units, and we'll talk a little bit more of this in a little bit. But that's basically how we use Newton's law of gravity. Basically, we're always looking at our Earth. We're going to assume the gravity on Earth is constant, which it more or less is, depending on where on Earth you are. So let's talk a little bit about the units. Okay, we are going to use both metric or SI units as well as your imperial or FPS units, customary units, English units, that sort of a thing. Okay, and most of you probably know these different things. So length is meter versus foot. Okay. Fortunately, time is the same each place. It's a second for each one. Now, the tricky part comes here when we talk about mass and force. Okay. So in SI units, mass is kilograms. Okay, and force is newtons. Okay, so mass again is how much matter something has or an object's resistance to acceleration or a change in velocity. Okay, Newton is the force applied to it. So if we think about Newton's second law, right, if I have 1 Newton applied to 1 kilogram mass, it'll accelerate 1 meters per second squared. Now, if we think about gravity, so the question becomes, okay, if I have 1 kilogram, how much does it weigh on planet Earth? What is the force due to gravity on that mass? So if I have 1 kilogram, okay, it actually weighs 9.8 newtons, or I can think about that the uh, gravitational force of the Earth is 9.8 newtons on the 1 kilogram. Okay, so the acceleration due to gravity is 9.8 meters per second squared. Okay, so that's the difference between a mass and a force. Okay, in imperial units, we talk mostly about pounds. Pounds is a force. Okay, a slug is a mass. 1 slug weighs about 32 pounds on planet Earth. The acceleration due to gravity in imperial units is 32.2 feet per second squared. Okay. Now, the problem that oftentimes happens here is people think of kilograms and pounds being interchangeable. They really are not, right? Kilograms are a mass, pounds are a force, right? Newtons and pounds can be interchangeable with a conversion factor. Kilograms and slugs can be interchangeable, but really you shouldn't be going from mass to force across units. Okay, you first should convert, the weight of an object, okay, into force using the acceleration due to gravity, mass times that gravity, either 9.8 or 32.2, to get to force, right? So analogous force in pounds, kilograms, and slugs. Okay, with this course, what we're basically doing is adding forces. So generally, we want to deal with newtons and pounds. So a lot of times, the first thing you do in a problem is switch over to either newtons or pounds, depending on what you're given in a problem. So just make sure you understand the difference between mass and force, weight. Okay, weight is the force on planet Earth of a specific mass. Okay. Um, any conversions, prefixes being like kilo, milli, mega, things like that, that you're more than likely familiar with. Those are all at the front of the book. We'll talk more about those in a little as needed. Any conversion factors in there, but to be honest, we don't usually convert between um, systems of units. Usually we stick an SI or we stick an imperial. The main conversion would be that gravity. If you want to go from mass to force on planet Earth, you use that gravitational constant that we've got there. So just quick thing on rounding. These are textbook problems, so we're not going to get too much into significant figures. Generally, if you round off to 3 significant figures on any problem, you should be fine. Don't do anything fancy with rounding, right? Just if it's 5 and up, round up. Below 5, round down. Okay, the one thing I do encourage you is don't do any rounding until the very end of the problem, right? You've got a calculator that can store like 10 digits. Keep them all in there until you get to the end of the problem and then do the rounding. Because every time you round, you create a little bit of error that can kind of build on itself as you move through a problem. So just be careful with that. Now, this does require calculus, but we will push calculus way off to the end of the semester. Okay. At this point, it's basically algebra. You should be able to know how to solve a system of equations, three equations, three unknowns, that sort of a thing. Um, that's going to be key to success. Trigonometry is also necessary immediately, however, not to the base that you learned when in trigonometry. All those identities you don't really need to know. If you remember SOHCAHTOA, where sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. Hopefully that's something that you recognize. That's really all you need to know with regards to trigonometry. Now, there are two laws that are very helpful. We will point them out when necessary. If it's not a big deal, you can write them down, keep them handy. That's the law of sines, law of cosines. Again, if you don't remember those, that's fine. We're going to give them to you, I think, actually in the next in the first lesson that we have. Um, so you don't have to remember all those weird secant squared over 2 equals the cotangent, blah, blah, all that stuff. I don't remember any of it either, right? So just the basic SOHCAHTOA and a couple of basic laws that will give you are really all that's necessary. So with that, that's kind of the background. We can go ahead and get started now and kind of start digging deeper into what we're talking about with statics.